What if space is never bent by mass and energy? If that is the reality, should we reconcile Einstein's general relativity with the flat universe? According to Einstein's general relativity, both space and time should be bent together by matter and energy. Space is rarely flat according to the theory. However, experimental data from various, independent sources confirm that the observable universe seems to be flat. That is, after going to all that effort to introduce curved spaces in general relativity, our universe remains flat. The curvature of space is zero. To make Einstein's theory work in many cases with observations, undetectable, superfluous dark matter and dark energy have been added to Einstein's equations. Dark energy makes up 71.4% of the universe, dark matter makes up 24%, and all regular matter adds up to less than 5% of the universe. All of them should add up to just the right amount called critical density, to make the universe flat. What if space is never curved by mass? What if there is no dark matter and dark energy at all? However, Einstein's general relativity is a very rigid theory. According to it, both time and space have to be curved by mass together. There is no way to get around it. You cannot have time curved by a massive object, but not space at the same time. Can we have a theory for gravity that is flexible enough to be fine-tuned to match observed data? The author postulates that, at the most fundamental level of nature, everything is made of particle waves and field waves. All of those waves are different excited states of a fundamental medium, traditionally called the ether. Those waves, either free ones or coupled ones, are propagating in space with the same pattern defined by a quadratic partial differential operator g mu nu partial nu. Gravity is simply defined as variations of the wave propagation parameters g mu nu in space and time. As a result, the space-time metric is defined as g underscore mu nu, the inverse of g mu nu. Simply put, curved space and time are simply a manifestation of non-uniform propagation of particle waves. The variations of g mu nu are caused by the presence of matter and energy or others. At any point of space-time, the propagation operator can be normalized to the standard form as -1 divided by c0 square, which is the standard speed of light, partial t square plus partial r square. It remains the same after the Lorentz transformation. That is exactly the reason why the laws of physics remain the same regardless of gravity and the relative motion of an observer. In terms of the universal wave propagation operator g mu nu partial mu and partial nu, the electromagnetic wave equation can be written as g mu nu partial nu axyzt equals to mu underscore 0, which is vacuum permeability, a physical constant, times jxyzt, where axyzt is a four-component vector field called the electromagnetic potential field. Jxyzt is a four-component vector field defining the electric current field. Following the same mechanism, we can postulate a gravitational wave equation as g mu nu partial nu a underscore gxyzt equals to 4 pi g, where g is the gravitational constant, also called Newton's constant, times j underscore gxyzt, where a underscore gxyzt is a four-component vector field defining the gravitational potential field. J underscore gxyzt is a four-component vector field defining the matter current field. G mu nu is a function of a underscore g. The new theory of gravity has the flexibility to fine-tune the function g mu nu a underscore g to match either Einstein's field equation where masses curve both space and time, or a new gravitational field equation where masses never curve space. In particular, for stationary gravitational fields, the curved space version predicts that g equals to -1/2 of c times the gradient of c. The flat space version predicts that g equals to negative c times the gradient of c. Here, g is gravitational acceleration, c is the effective speed of light. Both equations have the Newtonian gravity as their classical limit. Using existing astrophysics data, it is easy to check whether or not space is curved by mass. If g equals to negative c times the gradient of c, then the answer is no. Otherwise, if g equals to negative 1/2 c times the gradient of c, the answer is yes. We already know the gravitational accelerations g of stars in their home galaxies and the variations of the effective speed of light that cause gravitational lensing. To be more specific, we find the rotational velocities of stars in a galaxy using the 21 cm lines of the hydrogen atoms. From them, compute their gravitational acceleration rates using g equals to v squared divided by r. Compute the distribution of the effective speed of light field cxyz around the galaxy using gravitational lensing data. Check if g equals to negative c times the gradient of c or g equals to negative 1/2 c times the gradient of c. If existing observation data support the relation g equals to negative c times the gradient of c, then there is no need to make up 95% of our universe with undetectable dark matter and dark energy. Space is never curved by regular matter and energy. Einstein's general relativity is not compatible with quantum theory, another foundation of physics. The new theory doesn't have this troubling issue. Moreover, the new theory doesn't have many other troubling issues of general relativity like black hole problem, flatness problem, cosmology constant problem, singularity problem, vacuum energy problem, and quantum normalization problem. It is a call now to astrophysicists to check the relation using existing data at their hands to reveal the secret of the universe.